Okay, so I would like to just discuss some what I like to call knots in kinetics, in basic chemical kinetics. Okay, so generally, let me get a marker here. All right, so generally, if you have a reaction, let's say A, going to give you some sort of product P, right? uh, the effect of temperature on the rate of this process is contained in what we call the rate constant. Okay? Now, the rate of a chemical reaction, R, is basically equal to the rate or the change rather in the concentration of A with time. And you see that there's a negative sign here. Why is there a negative sign? There's a negative sign telling you that we are looking at a decrease in the concentration of reactant A over time. Okay, so T here represents time. Rate is also equal to the increase in concentration of the product over time, right? Let me just fix that D here, not looking so good. All right, that looks better. So the rate is equal to, all right, change in the concentration of the reactant with time, and we put a negative sign indicating that the reactant concentration, of course, square brackets here means concentration. So rate is given by a decrease in the concentration of the reactant over time, or an increase in the concentration of product with time. And so this is how the rate is considered for a chemical process. Of course, if you should try to plot this on a graph, what you do, let's say you could measure with time, if you could measure the amount of A in your reaction vessel or the amount of P in the reaction vessel, and so maybe what you could end up with are some concentration time values. Now, if you have some concentration time values, then you could do a plot. You could do a plot of concentration of A, right, with time versus time in seconds. Now, if you're looking at the reactant, which is A, then this is what will happen over time. The concentration of A will decrease over time. Okay, that is what is expected. Of course, you realize that at some point the graph starts to basically level out. That is because the reaction is approaching equilibrium, okay, as is typical. However, if instead of looking at the concentration or the change in the concentration of A, you decide to look at the change in the concentration of the product, which is P, with respect to time, then what you have a plot of P versus time, then you'll have a situation like this. Okay, there's an increase in the concentration of the product over time. So that is what is expected, and that's what you call a concentration time graph. Okay, now there are some other things that we should be aware of. Let me just point those out quickly. Okay, we want to keep this video short and to the point. Okay, all right. Now let's also remove this. Now let's say let's say this reaction, right? Let's say for this reaction, um, for a given time, right? Let's say A breaks down to give you 2 of P, okay? Let's say one molecule of A breaks down, right, in a certain time, And in that same amount of time, two molecules of P are formed. Okay, now the rate is equal to decrease in the concentration of A with time. But guess what? Guess what? Rate is not equal to, right, just the increase in concentration of P with time. Now, what is the problem here? Think about it. If this reaction let's say this reaction is running for 1 second, and let's say one molecule of A breaks down, okay? That one molecule will produce two molecules of P. So let's say it takes 1 second for one molecule of A to break down. In that 1 second, right, the concentration of A will decrease, whereas the concentration of P will increase. But guess what? If both of these are in the same volume, right, what you find is that the concentration of A will decrease by a certain amount, right, whereas the concentration of P will basically go up by 2 times that amount. Okay? Right. So what I'm saying is that in a given time, 2 times the amount, the process by which, or the rate by which P is being formed will be twice that, right, at which A is being used up. Think about it. When one molecule of A breaks down in a given time, let's say 1 second, in that same 1 second, two molecules of P will be formed. Okay? So let's fix this problem. Let's fix this issue. Here it is. Here goes. Here goes. We just put a half there. Okay? Yes. So basically what we have done is to level things out. Okay? Let's try to see if we can use an analogy to see if you can understand the concept of what is going on here. Let's say you're running a race with somebody, okay? And in 10 seconds, you are able to run 100 meters, okay? But, and this is you. Let's call you person A. That's what we are calling you, person A. Let's say person B, which is the person you're running with, in those same 10 seconds, person B is able to cover a distance of 200 meters. I am sure you would agree that person B is running at twice the speed of person A. Yes, of course. And that is what is happening here. In a given time, one molecule of A is consumed, and in that same time, two molecules of P are produced. It is clear then that the reaction, right? It is clear then that the rate of formation of P is twice that for A. And the only way that this can be true is if there's a half right here in front of the relationship for P. Right? And that's something important to understand. I hope that silly little analogy was able to get you somewhere in terms of understanding. Okay, let's look at something else. Let's go back to our same simple equation. A reacting to give us P, and of course we have our rate constant K. All right. Now, so let's say this is a first order reaction. First order. Okay, and the order of a reaction can only be determined experimentally. Okay, we can write an expression for the rate. Rate is equal to, let's say we're looking at a decrease in the concentration of A with time. Yes, let me fix this D. Seems I am not able to draw a D very well. Alright, let's try again. Okay, got it this time. So rate is equal to decrease in the concentration of A with time. This is also equal to K, which is the rate constant, times the concentration of A. If seeing that we stipulated that's a first order reaction, then we can put a 1 right there. Okay? However, whenever there's a 1 here, right, in the index, then we don't have to put it. It is understood that it is there. Okay. So this is basically what you call the rate law. That is what you call the rate law. Okay. We could play around with this equation a little bit, or this rate law a little bit, such that we get something which is a little bit more interesting, which is what we like to call the integrated rate expression for first order reactions. However, before I do that, let's mention some properties of first order reactions. Now, for first order reactions, we have to understand something. First order reactions, if you look, R here, if you look at this expression, R is directly proportional to the concentration of A. Therefore, if we should do a plot, right? If we should do a plot of, let's say, concentration of A versus rate, then what we will have is a line like that one, because there's a direct relationship between the rate and the concentration of A. What it means is that if you should double the concentration of A, then the rate of a first order process will double. Okay, there's a direct proportional relationship between the two. All right, let's get back to the integrated rate expression. Let's get back to see how we can play around with this rate law to get something that could be useful. Okay, now what we can do first of all is to just take this one, minus dA over dt is equal to Ka. Now I could do a number of things. I will multiply by dt. So this one will cancel with that one. I will also divide by A. So this one I'm just rearranging, that's all. Okay, so now I end up with minus dA over A, yes, is equal to K dt. Okay, we could also move this minus sign and put it over here. Okay, that's not a problem. So we end up with dA over A, yes, is equal to minus K dt. Now what we could do now is to integrate, right? We could integrate between limits of an initial concentration of A and a final concentration of A. Okay? Over here, we could do the same thing. K is a constant, so we could put that in front of the in front of the integration sign, and we could integrate from time equals 0 to some time later on called t. Okay? Now, after integrating this, what will happen, right? Because this is basically integrating 1 over A. What will happen is we will end up with ln a t minus ln a naught. There's a little step before this, but I kind of took that out to save you the pain. Minus kt. Okay, we could then rearrange a little bit by taking this one over the equal sign. Okay, so we have now ln a, this is a, yes, t is equal to ln a naught, yes, minus kt. Okay, this is a very important equation. This equation down here, very, very important. This is what we call the integrated rate expression for first order reactions. Now, what is so important about it? All right, so let me explain. Let's just put it back up here so I don't forget it. So it's ln at is equal to ln a naught minus kt. Okay, so this is the natural log of a at any given time, right, is equal to the natural log of the initial concentration of a, right, minus the rate constant times the temperature. Now, how can this even be useful? Now, remember our reaction. It was A reacting to give us P with some rate constant K. If during this reaction, you're able to measure the concentration of A, right? You're able to measure concentrations of A at different time intervals. Let's say at let's say at t equals 0, t equals 5, and let's say this is in minutes, right? Minutes. T equals 0, t equals 5 minutes, t equals 10 minutes, t equals 15 minutes, t equals 20 minutes. Okay? You are able to measure the concentration of A. Alright? And let's say you started out with about, let's say, maybe, let's say 2.4. Alright? And this is in, let's say, molar. 2.4, and then after 5 minutes, it is 2.1. After 10 minutes, it's 1.8. After 15 minutes, maybe it's about 1.5. I don't know. I'm just guessing some numbers here. And let's say after 20 minutes, it is 0.9. Okay? So you have now here some concentration values and some time values. Now, what you could do with these is just to take these concentration values, right? Take the natural log of all of them and do a plot. Do a plot, okay, of time on the x-axis, time in minutes, we're given in minutes, versus the natural log of A at time t. Now, when you do that plot, you'll get a line like this with a negative slope. But then you already figured that out by just looking at this equation. Now, that slope, right, is equal to k, the rate constant, minus k, I should say, the rate constant. Okay? The intercept, what do you think the intercept would be? The intercept is ln a naught. That's what the intercept is. Now, of course, when you try to find the slope of such a line, the value that you get will be negative. Let's say the value is negative, I don't know, let's say negative 0.2 or something. Minus 0.2 is equal to minus k, right? So clearly, k is equal to 0.2. It's a first order reaction. the rate constant as units of reciprocal seconds. Now, let's point out something. Rate constant cannot be negative. That's the first thing. Rate constant cannot be negative. Okay? So you can already kick away the negative sign, but it takes care of itself in such a question. So rate constant can't be negative. Another thing you should note is that rate constant is only a constant at a given temperature. If you change the temperature, then the rate constant will change. Let's say while collecting this data here, you change the temperature. If you change the temperature, then the slope of this line will change. Okay? Let me give you an example of such a thing. Let me explain a little bit better. Write back this equation so I don't forget it. Yes. Minus KT. Alright. And our hypothetical reaction was A reacting to give us a product P, rate constant K. Let's say you were doing this experiment at 20 degrees Celsius, and then something happened and you decide, okay, I'll do it at 30 degrees Celsius, maybe after 15 minutes, right? When you do your plot, right, you're working with two temperatures. I am telling you that once you change the temperature, the rate constant will change. That's no doubt. If you move from, let's say, 20 degrees Celsius, the slope would be maybe something like this. But the minute you change to a higher temperature, you end up with a steeper slope. Okay? Look at this. You will get one rate constant from here, minus K1. Because you change the temperature, the slope becomes steeper. The rate constant would have changed then. Right? Minus K2. Okay? And all of this was told to you by Arrhenius, because remember what Arrhenius says. Arrhenius says that the rate constant is equal to A, which is the pre-exponential factor, right? Or what you call it, the frequency factor, yes? Times exponential function minus EA over RT. That's what Arrhenius says, okay? You have the activation energy EA, R is the universal gas constant, T is the temperature, okay? A is the pre-exponential factor or frequency factor, and of course K is your rate constant. So Arrhenius gives you a relationship that tells you how the rate constant is affected by temperature. Now, look at this question. This question is it's a very interesting one. Let's say you're given some experimental data, concentration and also time data. And you were told that after 10 minutes, the temperature was increased from 20 to 30 degrees Celsius. Once you hear that, and remember, you must always work with your temperatures in Kelvin once you're going to make use of them. Once you hear that the temperature has changed, then you can automatically say to yourself that, look, there will be a change in the rate constant. Okay? There will definitely be a change in the rate constant. Rate constants, right? There's no if or maybe about that sort of thing. Okay? All right. So that's something you should bear in mind. Now, you could also be asked to calculate the activation energy from such data, I should say. Now, how could you do such a thing? How is such a thing even possible? All right, let me show you how. Okay, let's see. All right, so it's basically a subtraction. Take the Arrhenius equation. K is equal to A minus EA over RT. Take the natural log of this equation, ln K, yes, is equal to ln ln A, of course. All right. There would be a plus sign here, but seeing that this minus sign will come down, let me just write the plus sign anyway, but it's not necessary, but anyway. Minus EA over RT. Okay? Yes. Of course, there's a minus sign here and there's a plus sign. So what we could do is just to remove the plus sign. That's what I was saying earlier. We don't need to keep both of them. But the one that we need to keep of the two is the minus. What this is saying is that if you're given some rate constant values and some temperature values, right? Because remember, this equation can be written like, matter of fact, let me take off this graph so you don't get confused. Let's take this graph off. We don't want to get confused and lost. Okay? Just showing you how you can make use of this Arrhenius equation in calculating things like the activation energy. Now, this equation can be rewritten as ln K is equal to ln, hold a bit, um, okay, here I go, ln A minus EA, right? EA, activation energy that is, over R times 1 over T. These two are, this equation here is the same as this one. Now what this does is that it tells you that if you are given some rate constant values, then all you have to do is to do a plot like this one. Plot ln of the rate constant values versus 1 over T, right? And clearly, what you will have is a line with a negative slope. That slope will be equal to minus EA over R. And of course, the intercept right here would be ln A. All right? That's some important information that you can use the Arrhenius equation to get to. Okay? That's important. Let's say you're not given a series of rate constant values. Let's say you are just given two rate constant values, K1 and K2. Okay? You are just given K1 or K2. Let's say you are given data where the temperature was changing, right? Concentration time data where the temperature was changing, and so you did your plot and your plot had two slopes, right? And so you got two rate constants, I should say, sorry, K1 and K2. This would be T in seconds or minutes, whatever, ln AT, right? And now you're asked to calculate. Somebody is asking, oh, what is the activation energy? What is the activation energy? Then this is what you should do. K1 is equal to, let's say, A E EA over RT. Yes. Same thing here for K2. All right. You're probably wondering where I'm going with this. I'm going to take the natural log of both of them. All right. Natural logs of both of them. Okay. So now I end up with now ln K1 is equal to ln A. All right. Minus EA over R times 1 over T, and I'm going to call this one T1, yes? I'm going to do the same thing for the other equation, so I will end up with now ln K2 is equal to ln A. The thing is, I'm not going to label the pre-exponential factors A1 and A2 because if the temperatures don't change significantly, right, that is, if there's not a large change in the temperature, then the pre-exponential factors will not change significantly. Okay? So minus EA over R, right? Times 1 over T2. Now, what you could do is a subtraction. You could subtract these two equations. All right? You could subtract these two equations, and I guess probably you would want to subtract the one with 1, like ln k1 from ln k2. So this is what we'll do. Let's do it. Ln k2 minus ln k1, all right, is equal to ln a minus ln a. All right, of course, that cancels away. All right, and so EA over R for the same reaction, the activation energy will be the same. All right, for a given reaction, the activation energy is one activation energy. So we have now minus EA over R. So you don't have two activation energies subtracting each other and two R values subtracting each other. Those are constants. All right, they don't change. All right, unless you change the reaction, of course, which no, that's a different story. 1 over T2 minus 1 over T1. Okay, now you could be asking a number of things now. You could be asking a number of things in terms of this negative sign here. Okay, you could be asking what is going on for that negative sign. We could easily wrap up that negative sign. Look at what will happen inside here. T2 will be bigger than T1. All right, so if you have a large number, if you have 1 being divided by a large number, then clearly this side will become small compared to that side, and so you'll end up with a negative. However, if you flip them around, then you could get rid of this negative sign. Or if you say, look, you don't want to do that, fine, no problem. You could leave it. Okay? So you'll end up this part over here. You could fix it a little bit, so it looks a little bit more interesting. ln, as well as you could leave it. It's not a big deal. K2 over K1, yes? Because of course we know log in log difference is the same thing as ratio, is minus EA over R. Like I said, you could flip these two around, and so you could get rid of that negative sign. But if you can't be bothered with that, it's not a problem. It will not affect you. All right? And so if you have two rate constant values and two temperature values, right? R is a constant. You can easily calculate your activation energy. Okay? You can easily calculate your activation energy. Okay, let's talk about another simple concept before wrapping up this video, which is already becoming more lengthy than I wanted. Now, let's talk about the half-life. Half-life. Half-life is the time taken for the initial concentration of a species in solution, or of a species to decrease by 50%, or some people would say to drop to half. All right, it's the time taken for the initial amount of a species to decrease by 50%. Now, of course, we want to come up with some way to quantify this. Now, in terms of an equation, you could consider half-life, T represented by T half, is equal to the initial concentration of A divided by 2. If we are still using our hypothetical reaction, right? Here's our hypothetical reaction. So this is the definition of half-life. Okay? Now, let us remind ourselves of the integrated rate expression for first order reactions. Here it is. ln A naught minus KT. Okay? Now, what we will do here is to substitute this one here, where we have ln AT. Okay? We will also put this one, T a half, over here, because what we're trying to do is to create an expression for half-life. And seeing that we're dealing with a first order process, then we can do this. We can use the integrated rate expression for first order processes. All right, let's do that and see what happens. All right, and this can be done in a number of ways. I'm just going the simplest route, or what I think is the simplest route. Okay, minus k t a half. Okay, now we can do a little bit of a subtraction. Okay, ln, we'll just carry this one across the equal sign. Equal to minus k t a half. Okay, that is what we have. Now remember, subtraction in log is the same thing as ratio. So we could arrange these in the form of a ratio. ln, right? A naught over 2 divided by A naught, yes, is equal to minus k t a half. Okay? And so what we have now, cancel with that one. All right, and that might look a little weird because what we have is A naught over 2 divided by A naught. All right, but it is basically it's almost like flipping around and multiplying. All right, so the cancellation can really happen. So what we have left inside here is ln of a half is equal to, yes, let me just fix this a little bit. It's starting to get a little messy, all right, and hard to see. Let us not create a mess. All right, I'll just start back up here. All right, so what we have remaining is ln a half, all right, is equal to minus k t a half. All right, ln of a half is the same thing as saying ln of 1 minus ln of 2 is equal to minus k t a half. Ln of 1, I'm quite sure that will work out to be 0. So we'll have 0 minus ln of 2 is something like 0.693, I believe, is equal to minus k t a half. So what we have is a situation where we have 0.693, negative of course, is equal to minus k t a half, which is the same thing as saying positive 0.693 is equal to k t a half. Okay? You could rearrange this a bit to make the half-life the subject, which was our initial idea of getting an expression for half-life. Okay, so 0.693 divided by k. And this is the expression for calculating half-life for a first order process. Okay, look at the expression. What it means is that if somebody tells you the half-life, you could actually calculate the rate constant for a first order reaction. When you look at this expression, you can realize then that the half-life of a first order expression, or first order process rather, yes, is a constant. It is a constant. It does not contain concentration or anything like that. So the half-life for a first order reaction is a constant. Okay, because the rate constant is a constant at a given temperature. Okay, and so you could make serious use of this type of thing. How could you make use of it? Let's just point out a quick example. Let's say let's say somebody says to you that they found an archaeological sample, right? And it contains a certain isotope of an element, okay? And the element is known to have half-life of I don't know, I'll make up a number, 2,500 years, right? That is the half-life, 2,500 years. And they said that when they found this sample, it contained let's say 75% of the isotope. And now they're asking you, what is the age of this thing? What is its age? Well, radioactive decay follows first order kinetics. That's the first thing. So given that I have the half-life, I will go ahead and say, okay, half-life is equal to 0.693 divided by K. And since I have the half-life, I know I can find the rate constant. The rate constant then is, let's see, 0.693 divided by 2,500. And you can get your rate constant. Let's see if I can calculate that. Had to get my calculator. So it's 0.693 divided by 2,500. And we have, what's that? 2.772 times 10 to the minus 4. All right, let's fix that because I don't think you can see it well. Okay, let me just fix that. K is equal to 2.772 times 10 to the minus 4. And seeing that this is years and it's in the denominator, now it will become reciprocal years. Okay, all right. The next thing I could do with this is to take the integrated first order expression. All right, I could rearrange this expression a little bit by taking this part here over the equal sign. Okay, remember that the difference in log is the same thing as ratio. So I could write this one like this, ln at over a naught is equal to minus kt. Yes, the opposite of ln, right, natural log, is exponential. So I could write at over a naught is equal to the exponential, that one. All right, so this expression down here is what we will use. All right, okay, let's erase a little bit of this so we can see what is going on. We can have a little space to work. All right, so what's going on here? I think I messed something up. Great. All right, so I'm just going to make use of this expression over here. Now I have this part of the expression is important to understand. All right, look at this part. Look at this part over here. AT over A naught, right? The amount at some time later on versus the amount there initially. This is a percentage. It's not multiplied by 100, but it's a ratio of the amount that was there initially to the amount that is there now. That is the percentage decay, right, of the isotope, which is the same thing as 0.75. Where did that 0.75? Here it is, divided by 100, because this is a ratio. If you multiply this one by 100, then it's basically a percentage. Okay? Let me try to use an analogy. So you started out, let's say you're driving a bus. You started out with 100 passengers in the bus. This is AT. Not AT, but A naught, I should say. A naught, sorry. Let's say after 1 hour, right, you end up with only, let's say 50, let's say 30 passengers in the bus. Okay? How many passengers are left in terms of in terms of a percentage? It would be 30 over 100. Once you take that ratio, right, then you could multiply by 100 if you want a percentage. If you just want to look at the ratio to the amount there now to what was before, then you won't multiply by 100. It's the same type of thing. Okay, it's the same type of thing. Well, I hope that was a useful analogy. I don't know. All right, so it's the same thing. Here we go. E, I calculated the rate constant earlier. Minus 2.772 times 10 to the minus 4 times t. We don't know what t is. We don't know what t is. All right, that is the age. Okay. All right, no problem. Well, to get rid of the exponential function, let's take natural log of the 0.75. All right, and if we take natural log of this side, then this is what we end up with, minus 2.772 times 10 to the minus 4 times t. All right, it seemed we could have used this expression right here because we're going right back to it. Okay, let's see what the natural log of 0.75 is. Well, this is what I have. I have minus 0. Hold a bit, what am I doing here? Let us not make a mess. 0.288. All right. Now is equal to minus 2.772 times 10 to the minus 4 times t. Then clearly t is equal to minus 0.288 divided by, and remember this was in reciprocal years, right? Reciprocal years divided by minus 2.772 times 10 to the minus 4 reciprocal years. And so the answer will be in years, of course, because reciprocal years is in the denominator here. So let's see. Let's see what my answer will be. 2.772 times 10 to the minus 4. And now we have, this is what we have here. All right. I have something like there we go. 1037 years. All right. That's what we have. Okay. Okay. Of course, there are some other little tricks about first order kinetics that you should know. And one of the easiest ones I could point out in a few seconds is that Remember that PV is equal to nRT, right? Therefore, P is equal to nRT, and if you put the V here, N over V is the same thing as concentration, so P is equal to CRT, where C is the concentration. What I'm saying to you is that the partial pressure of a gas is proportional to its concentration. So instead of being given concentration values, you could be given the partial pressure of a gas. And you just use the partial pressure values as if they were concentration values. Okay? So just to point that out. Also, you should note that in a reaction, if you have a reaction A going to give you P via some rate constant K, if you are given the concentration values for the product, then you need to do some sort of subtraction to get the concentrations of the reactant, because you need to use a reactant. The integrated first order expression for these types of things deals with the reactant, okay, and not the product. And so you would have to do some sort of subtraction of the concentration of the product from, I guess, the initial concentration or something to get the concentration of the reactant. Okay, so just to put that out there. All right, take care. Good luck.